Hello, everyone.
Hello.
I hope you are all having happy days. I am. Anything new? No. All right. Well, let's go ahead and get started then. Make sure I have share the right screen. There we go. All right. Anybody have any questions? Anything, as we're getting into carbon chemistry, that's what you're going to be learning about next. So we're going to be talking a little bit about today. But first, before we talk about this really, really important branch of physical science, I want to do a little bit of a review. And then we'll talk about a little bit about carbon chemistry because it's just that important. It's been called the backbone of life. And the reason for that is because life on our planet wouldn't exist if it wasn't for carbon. So you're going to learn this week why carbon is so important. But let's do our review first. So let's see who we've got in class today. Well, let me pull that over, get that out of your way. Let's see here. So I think what I'll do is rather than using those teams, I'll just go with what we've got here. So I am going to do 3 teams because I think there's going to be some other students who join in, but that'll just put like 2 or 3 on a team. But let me go ahead and we'll start this way. We'll put Cecilia, Maxwell, Mason on one, and Sophie. No, I want just 3 on a team. And then here we'll do team 2. We'll do Sophie, Andre, and then over here we'll have Rita, and all right, Lucy James, you need to change your name. All right. You changing that for me? All right, so we were going to add, who just joined? Somebody just popped in and then popped back out. Not sure who that was. Thank you, Lucy James. Okay, I think I have everybody now. As other people come in, I'll add them to teams 2 and 3. So this is the way we're going to play. You guys are going to take turns. Okay, there's Maddie. Okay. All right, Maddie, are you okay with being called Maddie, or would you prefer Madeline? You originally.
Maddie is fine.
Okay, yeah, that's what I thought you said at the beginning. But I always want to make sure I'm calling you guys what you want to be called. All right, so the way we're going to play this Jeopardy game is you guys are going to take turns, 1 team at a time, choosing a category and a point value, but then anybody on your team can answer. So for instance, Cecilia will go first. Cecilia will pick a category and then a point value, but Cecilia, Maxwell, and Mason can all 3 answer the question that I'm going to ask, or that, that pops up there. Does that make sense? All right. The winning team, everyone on the winning team will earn 5 extra credit points. So one more second. Let me get one more thing arranged here. Okay. All right. All right. So we will start with Cecilia. Also, guys, help me keep an eye on the points to make sure that I add the points correctly. That I click on the points, like the plus sign, after your team wins. If I don't, let me know that right away. Okay, Cecilia, you pick a category up here and then the point value that you want down here. And I'm going to ask you guys to please not take a long time thinking about it. Eventually we're going to get to all these questions. So decide quickly so that we can keep the game moving.
I don't still really get it.
Okay, so have you ever played Jeopardy before? No. Okay. So pick one of these at the top. Which one of these are you interested in? Do you think your team might be able to answer a question about?
Maybe atomic structure?
Atomic structure. Now, do you want a 100-point question, a 200-point, 300-point, 400-point, or 500-point. Generally, they get harder as you go down. Not always. I did my best, but you know, a question is only hard if you don't know the answer to it, right? If you know the answer to all the questions on an exam, that exam's easy.
How about let's do 200?
All right. So at the end of the game, whoever has the highest point value is the winner. And that's the one who gets, that's the team who gets the extra credit. So atomic structure for 200, Cecilia? Okay. Here's your question. Now, Cecilia, Max, and Mason can all answer this. Electrons at different energy levels have different amounts of energy. Where do you find electrons with the least amount of energy? Cecilia, Max, and Mason. Mason.
Is it the first level?
It's the first level. It would be, where would it be compared to the nucleus? Closest or farthest away?
Closest.
Yes, it would be the first level closest to the nucleus. So all these right here would have a lot less energy than the ones that are out here do. Yep. All right. So now I give a plus to team 1, and you guys have 200 points. Then we go back here, and the next tip to go is going to be Sophie.
Periodic table 100.
What? That's really little. What do we call the rows on the periodic table?
So like the horizontal ones,
Yes.
periods.
They are called periods. Very good. The horizontal ones are called periods. All right, now Sophie's team gets 100 points. And next we start with Rita. All right, Rita, you need to choose a point value and a category.
States of matter for 300.
States of matter for 300. What state of matter has no definite shape and no definite volume? So Rita and Lucy James can both answer that. No definite shape. Lucy James.
Noble gases?
So this is not on the periodic table. I just want to know in general. Remember, we have different states of matter. There's, I can't tell you how many there are, but which one has no definite shape and no definite volume? All right, Rita, you want to help out? All right, I am going to put Jocelyn on your team. Oh, no, that gave you the answer. Well, you had already said gas, so I was going to accept that anyway. There we go. There we go. All right, so is everybody okay since she said gas, if I accept that? Okay, all right, so we're going to give team 3 their points. All right. Oh, Aisha is here, so I will add Aisha to team 1. Okay, so Max, you are next.
Let's do periodic table for 200.
Periodic table for how much?
200.
200. What do we call the columns on the periodic table? Go ahead, Max.
Groups.
We call that, yeah, you're glitchy a little bit, so I had to make sure I heard correctly. They're called groups. You could also have said families, either groups or families. All right, so Max's team gets the points, and now we go to Andre.
The periodic table 400.
Periodic table 400. What are the first 2 groups on the periodic table called? Andre.
Alkali metals and alkali earth metals.
Very good, very good. They are called alkali metals and alkaline earth metals. All right, so we're going to give Andre's team the points. You guys can see how the points are adding up now, so you get an idea. All right, now we go to Lucy James.
Periodic table for 300.
Periodic table for 300. What are the 3 categories of elements on the periodic table? Rita?
Metals, nonmetals, and metalloids.
Very good. Metals are on the left, non-metals are on the right, and metalloids are in those stair steps in between. So we will give Lucy James' team the points. All right, now we are back to team 1. It is Mason's turn to pick. Mason?
I will do periodic table for 500 points.
Periodic table for 500. Ooh, let's see here. What are the last 2 groups on the periodic table? Okay, Rita, you can't answer, so your hand needs to be down. All right, Aisha.
Noble gases and halogens.
Okay. Everybody okay? Everybody agree with that? So I didn't specify order. Just remember to make sure that the halogens come before the noble gases. But you're right, I didn't put them in any kind of order. So halogens and noble gases. All right, good job, Aisha. And now we go to Maddie.
Can I do physical and chemical change? 400?
What do we call the ability of matter to combine chemically with other substances? Anybody on Addie's team? Sophie, Andrew, what do we call the ability of matter to combine chemically with other substances? Sophie?
Reactivity.
It is reactivity. Very good, very good. All right, good job, Sophie. And let's give them the points. And now we are to Jocelyn.
States of matters 500.
States of matter, 500. List the 4 states of matter and tell which is rarely found on Earth. Anybody on Jocelyn's team can help. 5, 4, 3, 2, 1. Correct answer is solid, liquid, gas, and plasma. And plasma is the one that is rare on Earth. We don't find it out in nature. All right, now we go back to team 1. And Aisha, you didn't pick one yet, did you? No, okay, Aisha's turn then.
Phase changes for 500.
Phase changes for 400?
500.
500. What is the process in which a gas changes to a solid without going through the liquid state? Gas becomes solid without going liquid first. All right, anybody on team 1? Cecilia, Maxwell, Mason, and Aisha. 5, 4, 3, 2, 1. The correct answer is deposition. Deposition. All right, now we start with Sophie again.
States of matter 200.
States of matter 200. What state of matter has a definite volume and takes the shape of its container?
Liquid.
Yeah, that is a liquid. Very good. Liquid does that. All right, so Sophie's team gets the points, and now we are to Rita.
Phase
Ready?
changes 300.
Say it again.
Phase changes 300.
Phase changes 300. What is the process in which a solid changes directly to a gas without going through the liquid stage?
Sublimation.
That is sublimation. Well done. That's a cool term too, isn't it? Sublimation. That's why your ice cubes get smaller in your freezer. All right, so that was Rita's team. And now we are back to team 1, Max.
Let's do atomic structure for 300.
Atomic structure for 300. What do we call the region around the nucleus where the electrons are most likely to be? Cecilia,
Orbital?
everybody agree? Yes, it is orbitals. It is orbitals. Very good. All right, so let's give team 1 the points. Now we are to Andrew.
Phase changes 400.
What is the process in which a liquid changes to a gas without being hot enough to boil? Sophie.
Is it evaporation?
It is evaporation. Very good. That's how water gets out of the oceans and into the air. It doesn't boil, it just evaporates. And now Lucy James.
Phase change for 200.
When melting occurs, are the particles gaining or losing energy? Go ahead, Lucy James.
Gaining.
They are gaining energy. As they melt, they gain energy. They absorb enough energy to partly overcome the force of attraction holding them together, so they move out of their fixed position and slip over each other. All right, well done. Now we are to Mason. Try to decide quickly, everybody.
Let's do phase changes for 100.
In what phase change does matter change from a liquid to a solid as its particles lose energy until eventually the particles vibrate in a fixed position and are crowded closely together? Go ahead, Mason.
Would it be freezing?
Everybody agree? Yes, it would be freezing. It would be freezing. All right, good job, Mason. All right, now we go to Maddie.
Can I do physical change 500?
Physical and chemical change for 500?
Yeah.
Okay. What is the law of conservation of mass? Andrew.
Matter.
Oh, wait, Andrew. Oh, yeah,
Matter.
it's yours. Go ahead.
Matter can't be created or destroyed.
Yep. There's another part to that, though. It can't be created or destroyed, but it can.
Change.
Yeah, very good. Actually, I know right there it just says it can't be created or destroyed. So I would have accepted that. Remember that matter can change. We're going to learn later matter can actually even change into energy, but it can change form. It can change phase from solid to liquid, liquid to gas, back to liquid, back to gas. So yeah, all right, good job. All right, and Jocelyn.
Chemical, all right, let's do physical and chemical change 300.
What do we call the ability of matter to burn? It's one of the properties of matter. Rita, Lucy James, you can help out. All right, 5, 4. Oh, go ahead, Jocelyn.
Solid, liquid, gas, and plasma.
Those are the 4 properties or states of matter. Those are the 4 states of matter. This is one of the properties of matter. Whoop, I lost it. There we go. The ability of any of those, of matter itself to burn is called 5, 4, 3, 2, 1.
Flammability.
Flammability. That's called flammability. All right, now that was team 2. So now we go to Aisha.
Atomic structure 400.
Atomic structure 400. What do we call the electrons in the outermost energy shell?
Valence electrons.
Very good. We call them valence or valence electrons. Very good, Aisha. All right. Okay, now we start with team 2. We go to Sophie again.
Physical and chemical change 200.
What is defined as anything that has mass or volume? Andre.
Matter.
Matter. Yeah, matter is anything that has mass or volume, takes up shape or space. Good. All right. So that was Sophie. Now we go to Rita.
Atomic structure for 500.
What must happen for an electron to jump to a different energy level? Five, 4, 3, 2, 1. It has to either lose energy or gain energy. If it's on one of those at the outer shell and it loses energy, it jumps down to a lower one. In order to jump up to a higher one, it has to gain energy. So energy is involved there. All right, that was Rita. Now we go to Cecilia. You guys, you see these two over here? Nobody's picking the chemical interactions. You can see them on your screen, right? They just look a little scary. Go ahead, Cecilia.
States of matter 400.
What state of matter lacks a fixed volume and fixed shape and consists of charged particles?
Gas.
Everybody agree? Maxwell, Mason, Aisha? Max is saying no, or Mason is saying no. All right, we're going to take gas. It is actually plasma. That's what makes plasma different. Just like gas, it does not have a fixed volume. It does not have a fixed shape, but it's those charged particles that make it plasma. That's what makes it different. All right, that was Aisha. Now we go to Andre.
Chemical interactions 1, part 1, 300.
300. What kind of bonds are forces of attraction between positive metal ions and the valence electrons that surround them? What kind of bond? Positive metal ions and the electrons around those ions. Sophie.
Metallic bonds.
Yeah, it's a metallic bond. Very good, Sophie. All right, now it is Lucy James.
States of matter for 100.
States of matter, 100. What state of matter has a definite shape and a definite volume? Rita and Jocelyn can help. Which state of matter has a definite shape and a definite volume? Jocelyn.
Maybe gas?
Gas? What do you guys think? Lucy James, Rita, you want to go with gas? Lucy James, you're shaking your head.
I think it's solid.
You think it's solid? All right, we got a gas and we got a solid. Rita, you're going to be the tiebreaker.
I think it's gas.
You think it's gas. All right. Oh, it's actually solid. Lucy James had it. Remember, gas goes everywhere. It doesn't have a definite shape. It kind of changes shape as it floats around. It has no definite volume. It just goes out into the atmosphere. Solid, though, has a definite shape. A solid doesn't change shape unless you change the energy that it has. And it has a definite volume. All right, here we go. Now that was Lucy James. So now we are back to Max.
Chemical interactions, part 1 for 500.
All right. What would go here? Reactants, yield. Aisha,
Products.
products. You got it. Reactants react to produce the product. Very good. All right, so that was team 1, right? Yeah. Okay. Now we're at team 2. Maddie.
Can I do chemical interaction part 2? 500?
500.
Yeah.
When is a chemical equation balanced? Andrea?
When it has like the same amount of both elements on each side of the equation.
Yep, very good. You guys all agree? Yes, it is balanced when both sides of the equation have the same number of atoms of all the elements in the equation. Excellent. All right. Now we are to team 3, Jocelyn.
Physical and chemical change 100.
Physical and chemical change for 100. A change in one or more physical properties of matter without any change in chemical properties is called a what change? Rita, Lucy James, Jocelyn, you can all answer. All right, 5, 4, 3, 2, 1. Correct answer is physical. It's a physical change when it's only the physical properties and no change in the chemical properties. All right, Mason. Can't hear you, Mason.
Chemical interactions part 1 for 400 points.
What do we call bonds between atoms that do not share electrons equally? Anybody on team 1 can help. Mason.
I'm going to say polar covalent bonds.
You're going to be correct. Polar covalent bonds. Very good. All right, now we go to Sophie.
Chemical interactions, part 2, 300.
Reactions that release more energy than they use are called Andrea.
Exothermic.
Exothermic. Energy is coming out. They are releasing energy. So energy is coming out. It's exiting that reaction. Team 3, Rita.
Chemical interactions, part 2 for 400.
A reaction in which a fuel reacts quickly with oxygen and produces carbon dioxide and water is called a what? What's it called? 5, 4, 3, 2, 1. It is called a combustion reaction. You have your fuel, in this case it's the candle and the wick. You have oxygen from the atmosphere. Carbon dioxide and water are both coming off of that flame. All right, now we go back up to Aisha.
Chemical interactions, part 2, 200.
A substance that increases the rate of a chemical reaction is called a what?
A catalyst.
It's called a catalyst. Anybody remember what catalysts are? Let me give Aisha's team points. What the catalysts are called in the human body or in living organisms? Andrew?
Enzymes.
Enzymes. Yeah, that's right. All right, so that was Aisha. Now we are to Andrew.
Chemical interactions, part 1, 200.
What kind of bond forms when a metal transfers valence electrons to a nonmetal? Anybody on team 2? Sophie, Maddie, you can help him out. Sophie.
Ionic bonds.
Ionic bonds. Yeah, it's giving one of its valence electrons completely over to the other one. So it has one less and the new one has one more. That makes them slightly negative and slightly positive, so they stick together. That's the strongest kind of bond that we have. All right, and we'll just do one more now. We'll do, it is going to be Lucy James' turn to pick.
Atomic structure for 100.
Name the 3 parts of an atom and give their charges. Rita, Jocelyn, you can help. 3 parts of an atom. All right, 3, 2, 1. The 3 parts of an atom are protons, electrons, and neutrons. Protons are positive, neutrons are neutral, they don't have any charge at all, and electrons have a negative charge. All right, so our winners with 3,500 points are Sophie, write your names down, Andrew, and Maddie. You will each get 5 extra credit points. I'll add them to that extra credit lesson that we have there. All right, let's just see what the other 2 questions are. See if you guys can answer them. What kind of bonds form when nonmetals share valence electrons? Anybody just yell it out.
Covalent bonds.
Covalent. You got it. Share, they cooperate, and then valence electrons. Covalent. Very good. Oh, I guess I should show you that. Right there, covalent bonds. And the last one is, what do we call the energy needed for a chemical reaction to begin? You have to put a little energy into any chemical reaction.
Activation energy.
Yeah, it's called activation energy. Excellent. All right. Good job, everybody. Well done with that one. Let's see here. Here we go. All right, so I want to give you guys just another heads up. There's going to be a lab that we're going to do together in class next week. Now, again, it's not marked as required, so you don't have to do this, but it's always better if you can. Always better to do the lab instead of just watching me do the lab. But I'll be doing it. Either way, though, I want you to print out the lab sheet that I'm going to send you tomorrow. You don't have to write anything down today because either later today or tomorrow, you're going to get a lab sheet in the announcements from me. Now, this is the list of supplies that you'll need right here. There's nothing really unusual that you have to order, but there might be something that you have to go to the store and buy. Like you might not have liquid starch, but you can get it at a supermarket. And the best brand to use is Stay-Flo. You might not have vitamin C tablets or these juices right here. But if you do, great. If you don't, you can get them. And I will send you this lab sheet. It'll have all of the instructions on it for what we will do together. And then it will also have this data collection sheet So this is the part that you need to make sure that you print and bring to class, because you'll write these down, the data collection stuff, you'll write them down as we do the experiment. Again, watch your announcements later today or tomorrow to get them. Your printer is broken. That's okay. See how easy this is? You can just write that on a piece of paper. This is all you really need to have. You don't have to write all of this down. But if you can put this on a piece of paper, that's fine. That's all you need to do. Okay? Now let's talk about this amazing, amazing, amazing element called carbon. Because of its unique ability to combine in many ways, both with itself and with other elements, carbon has a central role in the chemistry of living organisms. So take a look there at the carbon on the periodic table. Look at the cell. What's the atomic number of carbon? Andre?
6.
6. What's its atomic mass? Aisha?
12.011.
Yep, very good. Now, what group is carbon in? Mason?
The carbon group.
Yep, it's in the carbon group. What number group is the carbon group? Cecilia?
14.
14, you got it. So all of the elements that are in group 14 are called the carbon group because carbon's at the top right there. So what period is carbon in? We know what group, what period is it in? Andre?
2.
2, you got it. How many valence electrons does carbon have? Andre?
4.
It has 4. You got it. It has 4. How many does it want to have? Mason?
8.
8. They all want to have 8. Remember that. I want 8. Almost all of them want to have 8. So it has 4. It wants 8. So how many bonds can it form? Andre?
4.
It can form 4 bonds. Remembering this picture will help you to remember that. Picture carbon with 4 arms. Each of them really, really wants to be holding hands with another atom. Carbon can form up to 4 bonds. So remember when we're talking about bonds, there's 3 kinds of bonds. We learned about those, the 3 kinds of bonds. We talked about them in our review just a minute ago. Somebody tell me one of the 3 kinds of bonds that atoms can form with one another. Andre?
Covalent.
Covalent. I got to turn off my pointer here. There we go. Covalent bonds. That's where 2 nonmetal atoms share their electrons. What's another one? Mason?
Ionic bonds.
Ionic bonds. Yeah, ionic bonds is where a metal donates an electron to a nonmetal. And then what's the last one? Cecilia?
Metallic.
Metallic. Yeah, I think metallic's really cool. Picture a sheet of aluminum foil, right? That is an example of a substance that is held together with metallic bonds. Now, if you could get down to the atomic level, what you would see are all these ions and their electrons are just changing form. They're just moving around. Think of them as like little fish that are swimming around among the ions. They move pretty freely. I think that's pretty cool to think that's happening in something as solid as a sheet of foil. Now, we also talked about hydrogen bonds. We call them hydrogen bonds, but they're not really bonds. They're not as strong as bonds are. We can think of them more like a force, but because hydrogen, that connection with hydrogen is so important in living things, we call it a hydrogen bond, even though it is a little bit different. And it's really important in water molecules. It's important in protein molecules, in DNA that is inside the nucleus of your cells that gives you all the characteristics that make you you. All right, so carbon. What kind of bond does carbon form? Only one of them. Remember the 3 kinds? There's only one that carbon forms. Mason?
Is it covalent?
It is covalent. Look where it is on the periodic table, right here. Let me get my pointer again. Right here is where carbon is on the periodic table. Remember, it has 4 valence electrons. All of these have 4 valence electrons. It does not want to give up 4, and it doesn't want to gain 4. That takes too much energy. So what it wants to do is share. And shared bonds are what we call are called covalent bonds. Now, what's really interesting about carbon is that it can form single bonds, double bonds, or triple bonds, both with other carbon atoms and with other elements. Now, this is a single bond right here. It's pretty strong. A single covalent bond, not as strong as ionic, but still pretty strong. But look at this one right here. There's 2. This is called a double bond. An interesting thing about a double bond, it's not like 2 single bonds. It's not twice as strong as a single bond. And that's because that extra bond that it has in there isn't as strong. It's a little bit weaker. So that the second one is pretty easy to break. And when we've got 3 right here, one of them is really strong. The other 2 are pretty easy to break. You can kind of think of these bonds as being like ropes that, hold 2 mountain climbers together. So one thick rope would be our single bond, and then there might be a thin backup rope that they would have. And if it's triple bond, it's got 2 thin backup ropes. So that ability to form these single, double, and triple bonds lets our carbon atoms join together with other atoms in order to form chains that are really long, almost unlimited in their length. They can bond with other carbons, they can bind with other elements, they can make straight chains or chains that have branches off of them. They can even make rings. So carbon always wants to have 4 bonds, always. It's got those 4 hands that stick out that always want to form more, 4 different bonds. All right, so here we can see we have a substance called butane. This is the chemical structure of a butane molecule. Somebody tell me the formula for this one. What is the chemical formula for butane? Mason.
Is it C4H10?
That's what it is. Now, the way Mason got that, he counted up the carbons, C4, and then H, there's 4, 5, 6, 7, 8, 9, 10. C4H10. So this is butane. This is what you might have in your lighter, or maybe something that lights your grill. If you have a gas grill, like a lighter that people would open, that's got butane in it. Here's another one. This is another carbon-containing molecule. It's called hexane. What's the formula for hexane? Cecilia.
C6 and then H14.
That's it. There are 6 carbons and 14 hydrogens. So the chemical formula is C6H14. Now, hexane is used to pull the oil out of seeds. Like if you have ever seen corn oil, corn is a seed. How do they get the oil out of a seed? They use something like hexane in order to do that. Hexane also smells nice, so it's probably in perfumes that you might use, or anything scented. Scented candles might have hexane in it. Here's another one. Look at the shape of this one. This is what we call a carbon ring. What's the formula of this benzene? What is the chemical formula? Andrew,
C5H6.
count again.
Oh, C6H.
There you go. You got it. So look how every carbon there, every one of them has 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Every one of them has 4. Some of them are double bonds though. So carbon is able to form double and even triple bonds. So benzene is used to make plastic and rubber, even detergents and pesticides use benzene. So again, the double bonds here, they're stronger than the single bonds are, but they're not twice as strong. They're like, one and then a little bit more. They're like the backup bond that they have there. All right, now let's talk about what it means to be organic, because in life, when you're talking about something organic, you generally, well, what do you think? Somebody tell me, when you think of the term organic, what do you think of? Mason.
I think of like the brand organic that you'll find at the grocery store where it's
Yeah.
grown with like no chemicals and it's non-GMO, where
Right.
just like the bare bones for it.
Yep, yep. That's what most of us think of when we hear the word organic. That's not what organic means in chemistry, in science. In science, the word organic means that it has at least one carbon atom in it. So we often call carbon chemistry organic chemistry. When you get to college, you may take a class called organic chemistry. It's basically carbon chemistry. And yeah, we're going to study carbon chemistry in our class for about a week. You can study carbon chemistry for a couple of years when you get to college. That's how complicated carbon chemistry is. But just remember that organic means it has at least one carbon in it. And look at that. Carbon is able to form millions of different compounds with other elements just by bonding with those other elements. So here we can see glucose. Glucose is the sugar that is made in photosynthesis. When the sun shines on a plant, it shines on the cells of the plant, and inside those cells there's an organelle called a chloroplast. We'll learn about this later, but a chloroplast takes that energy from the sun and converts it through a process called photosynthesis into this sugar that's called glucose. Now plants can also, they can alter, they can make changes to that glucose to make other sugars too, like fructose. Fructose is a fruit sugar. So the fruits that you eat would be higher in fructose. But all plants make glucose. But look, we can see there's at least one carbon, at least one carbon. Now there's more, we got a carbon chain here. But once again, notice every single one of these carbons has 4 bonds. Even this one right here, because it's got a double bond with that oxygen right there. All right, now, carbon can do a lot of things. It can bond with itself when there's nothing else in the element, no other in the molecule. There's only carbon bonded to other carbons. We call that the pure form. And the word allotrope just means different form. So these are different ways that pure carbon can bond with itself to make different things. And we think there are as many as 500 different allotropes of pure carbon. These 3 are really common ones, though, that people work with. So sometimes we call these forms crystalline carbon because they can form crystals. So diamonds are a kind of a pure carbon. Graphite is a kind of a pure carbon, and a Buckminster fullerene, that's a strange name, but that's a kind of pure carbon. Mason.
This isn't a question, but it's a cool fact I learned that you can do. So if you get if you get Scotch tape and a pencil, you write a bit on the pencil, on the tape on one side, and you keep sticking and unsticking the tape together on both sides. If you do it enough times, you will get graphene.
Is that right? I hadn't heard that before. That's very interesting. Very interesting. So here you can see, I said there are many as 500. There's just a few more that are more commonly known. Diamond, fullerene, Buckminster fullerene, Lonsdaleite. I'm not going to read all of those, but you can get an idea right there. So there's the graphene that Mason was talking about. Graphite apparently can turn into graphene. So I'm going to look that up, Mason. Hold on. All right, let's ask about this. Can you turn graphite into graphene with tape and a pencil? Let's look and see what, well, it's not going to go. Yeah, so technique was used in 2004 to isolate graphene. So here's what you do. You take your piece of tape, stick it to the surface of the graphite, then peel the tape away. This will tear off some of the top layers of graphite, which is mostly made of graphite flakes. To get thinner and thinner layers of graphite, you fold the tape, press it back onto the graphite, and peel it off again. With each peel, you're separating the graphite into thinner layers. Eventually, you might get a thin monolayer of graphite. That means just one layer of molecules. That is the graphene. A single layer of graphene is incredibly thin, just one atom thick, and can be quite difficult to see with the naked eye. But under a microscope, it should be visible as a single layer of carbon atoms. Sometimes you can also see the difference in thickness if you put it on a silicone wafer. We don't have any of those. So yeah, that's very cool, Mason. Have you ever done that? That's very cool. You'd have to have, I think, a pretty powerful microscope in order to see a single layer of carbon atoms, but that's pretty cool. All right, so let's look at diamonds. Diamonds are a crystalline form of carbon. Each carbon atom is bonded very strongly to 4 other carbon atoms. So this is formed with high temperature and high pressure. I want you guys to see how diamonds form.
On a chemical level, a diamond is just a bunch of carbon atoms bonded together in tetrahedrons. This crystal structure is why diamond is the hardest natural mineral, and it beats most man-made ones too. So we know that diamonds are special, but where do they come from in the first place? Diamonds are formed in really extreme conditions, which is why you might find them at the sites of asteroid impacts and even on meteorites in space. But we think most natural diamonds were made millions, if not billions of years ago in the splooshy molten rock deep within the Earth. Over 160 kilometers beneath the Earth's surface, the intense heat and pressure forced carbon atoms into that tetrahedral structure to form diamonds. And then, deep volcanic eruptions blasted them up to the surface at around 40 kilometers per hour. If the diamonds came up much slower than that, the gradually decreasing pressure would let the carbon atoms shift back into other stable forms like graphite. At the surface, everything cooled really quickly to make these igneous rock formations called kimberlites, with diamonds hiding inside. And eventually, we humans came along to mine them. So we know that diamonds are made of squished and superheated carbon atoms, but we're not exactly sure where that carbon came from. Geologists have 2 main guesses. For one, there could be some kind of carbon-containing sediment deep within the Earth's mantle that never saw the light of day. Or maybe the carbon in diamonds came from organic stuff in subducting tectonic plates, like stuff on the ocean floors, but not coal. That whole all diamonds are just coal under pressure thing is mostly just wrong. See, coal is a form of organic carbon, but it was made mostly out of ancient plants in layers of sedimentary rock closer to the Earth's surface. So it formed way later and way higher up than we think most diamonds did.
All right, so cool. All right, the next one is graphite. So in graphite, every carbon atom is bonded tightly to 3 other carbon atoms, not 4 like in diamond, 3. Graphite makes the lead that you have in your pencil. It also is used for lubricants in machines and things like tennis rackets and badminton rackets. And then we have those fullerenes. Those are hollow tubes or spheres. Nanotubes are tubes, fullerenes are spheres. And these are made in a honeycomb shape like this. So you can see how they're built into almost this perfect honeycomb shape. They have almost no imperfections, so they're very, very strong. They're almost impossible to break. So they're shaped a little bit similar to a honeycomb, and honeycombs are known to be very, very strong. The hexagon shape makes them really, really strong. So let me see here. Here are some things that we use nanotubes for. So scientists use them to make things stronger. They can use nanotubes as ways to get medication to a cell in the human body. They're used in solar panels because they're really good at absorbing ultraviolet light. They're used for water treatment, as you can see there, electrical applications. So the exact shape of the nanotube is kind of hard to make, so they're still really expensive. They're hard to make and very expensive, so we don't see a lot of widespread use of nanotubes yet, but we will. As time goes by, we will see them. For some reason, it's kind of interesting. If you bring a bunch of nanotubes together, they change their shape. Their properties change, and they don't work the same way that they did before. So we got to fix those problems in order to be able to use them more. So, all right, we are out of time for today. Anybody have any questions? All right, great job on the game today. Andrew.
I don't exactly get how the single, double, and triple bonds work. Like, is there a difference between them?
There is a difference between them. You'll learn the difference between them in a high school physics class. For our purposes, they're different. So they're all covalent bonds, but they're a little bit different than one another. The first bond is, think of it like being a thicker bond. It's not really thicker, but it's stronger. The double one has another, like not quite as strong a bond. And then the third one has another not quite as strong bond. So it's like, trying to think of another example other than the rope, but you know, it's like if you were a rock climber and you're rappelling down a rock, and you've got one rope that you're using to rappel down the side of the rock. That's a strong rope, but you might want to have another one that's just your backup rope. It's not as strong as the first one, but it's there just in case. And then if you are really worried, you might have two backup ropes, but they'd be thinner than the first one. So they're easier to break. That's the difference between them. Do you want more detail than that, Andrea?
I'm just wondering, like, why would there be like 3 instead of 1? Like, what's the reason for it?
So partly because carbon has to form 4 bonds. So yeah, it's got to have 4. So it makes that second bond or third bond in order to be stable, in order to have a stable outer electron valence shell.
So it's for stability mostly.
Primarily it is for stability.
Okay.
I'm going to do a little research this week, Andrea, and if I find out anything different than that, I'll tell you next week in class or send you guys a message, okay? Yeah, excellent. Mason.
What is the most complex carbon molecule there is?
Probably, well, certainly in a living thing, it is a DNA molecule. DNA is the most complex one that we have. What is the most complex carbon molecule? Let's see here. Macromolecules, fullerenes, carbon nanotubes, graphene oxide, polymer carbon compounds. Those would be like plastics. Graphene, there's a lot of them. They're not giving us the most here. While DNA is the most complex biological molecule that contains carbon, carbon nanotubes and fullerenes are some of those complex pure carbon molecules in terms of their size, structure, and properties. Yeah, so one of them doesn't really seem to outweigh the other as far as complexity. Yeah, DNA is that's the one that your genetic code is DNA. It's inside the nucleus of all your cells, and that is what makes you who you are. Yeah, great question. All right, everybody, have a great week. I'll see you next time. Thank you for coming. Bye.